All right, welcome to the final class in all of the airframe and power plant curriculum. So this is kind of where we've been going the entire time, and you've developed a lot of skills all the way up to this point. This class isn't going to necessarily, I don't think, give you anything new in terms of things that you'll be able to do, but it will refine your understanding pretty significantly on turbine engines and how they play a role, and on aircraft that are powered by turbine engines. The turbine provides air power, electrical power, hydraulic power, all that good stuff. Either in the from the APU or either one of the main engines. And so with that, we're just going to start by just kind of an overview of turbine engines, like what's the theory behind it, how do they work, what are some of our key components, and then we'll progress on.
Okay, so up to this point, we've really talked a lot about reciprocating engines. We've talked about their four cycles: the compression stage, the combustion stage, the expansion stage, or the power stage, and the exhaust stage. Um, there's nothing different or new that's happening with the turbine engine. The key difference is that in a piston engine, everything is happening in its own event. So you have a compression stroke, you have a combustion stroke, you have a power stroke, and you have an exhaust stroke, meaning that the piston is going up and compressing the gas in one moment, and then it's going to spark. It's going to light the fuel air mixture, and then in a completely separate event, it's going to then generate power as the piston comes down, and then it's going to come back up, and it's going to have an exhaust event where that's the only thing that the piston is doing. It's just pushing that exhaust out, and so on and so forth. Those individual events in a jet engine become one continuous event where everything is happening simultaneously. So as the exhaust stroke is happening, it's not, which is not a stroke, but the exhaust event rather is happening, then so is the compression event, and so is the power event, and so on and so forth. If you look at this diagram of this cutaway of this turbofan engine, imagine you're the air that you're coming in. Now, what for right now we want to pay attention to, like on the left hand side, the blue lines that are on either side of that of the spinner. All right, that air is going to come in to that first set of turbines. All right, and it's what's going to happen is it's going to start to be compressed. Now, just like we do with pumps, as that air molecule comes in, it's going to get compressed a little bit, and then it's going to go into a tighter space, which is going to compress it a little bit more, which is going to go into a tighter space, which is going to compress it a little bit more. And this is how we have like stator vanes and turbine vanes, and we'll get into that here in just a little bit. As it squeezes it down super, super tight, it's eventually going to roll down into the combustion section, or you'll hear people refer to the hot section, because that's where the actual fire happens. And in there, you're going to have these igniters that also have spray nozzle or fuel spray nozzles next to them. So that super compressed air is going to get sprayed with fuel and to give you that 1-to-1 ratio. And then there's an igniter right there that's going to spark it. And when it sparks it, it's going to explode. And when I say explode, I mean it literally explodes. It creates a ball of fire. Now, this is also different than on a reciprocating engine. A reciprocating engine wants a good, clean, steady burn, and it doesn't want like an explosion. If you have an explosion happening, then that's what you call detonation, which can damage the engine. But on a turbine engine, it's the exact opposite. They want the explosion. They want it to be like this one big boom, and then as the engine continues to go on, the explosion just basically never stops. It's just constantly going. And so as that happens, the air is going to want to expand rapidly, but it can't go anywhere because the super compressed air is being pushed in. So the only way for it to go is out the back end of the turbine. Now, a lot of people think that they see the big flames come out of these jet engines and all this other good stuff, and they think that that is where the thrust comes from. And that's true. Thrust does come from that on a turbojet engine. But a turbojet engine is absolutely not economical in terms of fuel, and it's fairly rare. Like most of them now are limited to just military applications, and that's it, where you need a lot of power, and we don't really care about how much it costs. Most of the other engines we'll get into in a minute are turbofans or turbojets or not turbojets, but turbo shafts and that sort of things. And so where like what do where does the power for your typical engine that you would see in a heavy commercial world look like? Where does it come from? And it comes from this last section of turbines, just like the on the front end of it, how it compressed the air down in the compression section. As it goes through that power section, it's going to start to spin those turbines as it leaves. As it spins that turbine through all of those different stages, it's going to spin the shaft that's in the center that runs through all of this. Because in the center there's this shaft. Now, as that spins, it's going to then turn around and compress the air on the front. So if you all remember talking about turbos in reciprocating engines, this is very similar. Like the exhaust spins one set of turbines, which then turns the turbines on the front of the engine, which helps continue the whole process. So once this thing lights off, it just becomes this like just running machine that will just go until you disrupt the fuel flow. Basically, is how it stops. Um, so like the idea of like suck, squeeze, bang, blow happens here, but it's happening continuously. It's going to suck the engine in the front. It's going to squeeze it right there. Those compressor scrolls or in the turbine section or the compressor section, and it's going to bang in the hot section. And it's going to blow it out the back end, and as it blows out the back end, it's going to spin the turbines, which then perpetuates the whole machine. It just keeps on going. It'll just go like that forever until something either breaks or you cut the fuel for it. They're very, very interesting machines. They're actually a lot simpler than piston engines. People will get all wrapped around the axle about the precision measurement that has to happen in a turbine engine, and that's true. They like it nowadays. Like they've got the turbofan engine specifically has been engineered to the nth degree, and you're going to have all kinds of good, great engineering that happens in there, and super precise measurements that take into account the expansion of the blades due to heat or centrifugal force, and how the fan cowl expands with it, so that way it keeps the same distances. Stuff is fascinating. But when it comes right down to it, it's actually a simpler engine because you have like one crankshaft that's basically doing everything, and you don't have any pistons moving up and down with valves and all this other kind of stuff. You just simply have like one continuous flow. It's very, very simple in concept. And so that is the basic theory of it. Now, we're going to turn around and we're going to apply this in multiple different ways through using the power that's generated on that center shaft. So now let's talk about components, and then we'll get into application.
All right, so now that we have a good understanding of how a turbine engine works and what sequence it works in, let's start looking at like the internal components. Like what is happening inside of that engine?
Okay, so let's talk about the first component is the air inlet. How does air enter into the engine? Now, you would be surprised the level of engineering that goes into just answering that question. Like, how does air come into the engine? Because the engine air needs to be at a certain pressure and a certain temperature in order for it to be compressed effectively, so that way it can burn effectively. Now, you're all probably familiar with the engine on the top left-hand corner, or at least the design of it. That's your typical CFM 56 you'd see on like a 737, that sort of thing. That's going to be common on all your heavy commercial aircraft. Now, you wouldn't know it, but there's actually little holes all the way on the inside of that inlet cowl, and the curvature of that cowl is built in such a way to create shock waves to slow the air down to help drop the pressure, so that way it can be compressed, effectively at a certain temperature and all this other good stuff on there. And there's like this untold amount of math that goes into designing those cowlings. It's not just simply like kind of willy-nilly, let's put it together. Now, that one in particular is for subsonic, so below the speed of sound, where air behaves a certain way. As you start going faster, and this is going to be something that's going to be very relevant for your careers, because now we're starting to see supersonic flight come back into the civilian space. And it's not just for missiles and military jets, but rather like you're going to see boom supersonic. There's other companies that are in the works to talk about like delivering private supersonic jets. you start to see these other cowlings start to come into being. So you have a rectangular supersonic cowling there, and then you have an asymmetric or axisymmetric supersonic cowling up top that you see on like the SR-71 or whatever. Those air inlets are designed to create shock waves to penetrate the air at certain speeds in certain ways, so that way it will actually be able to be compressed. So this is actually the first stage of the whole turbine concept, is just like the air coming into the engine. Okay, so the next stage beyond the air inlet is going to be the compressor section. Now, this is going to look very different depending on what type of engine you're dealing with. This is just an example from an old NASA slide to show you how the centrifugal compressor and axial compressors will look like. But essentially, they all do the same thing, no matter what their configuration is. They just take the air that's coming in, and they begin to squeeze it, and they squeeze it and 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 squeeze it until it's at the right pressure, temperature, everything for combustion. Now, there's two different kinds of compressors that you'll have. First off is the centrifugal flow compressors, and that's what you're looking at right here. The centrifugal flow compressor consists of an impeller, which is a rotor, and a diffuser or stator, and a compressor manifold. The centrifugal compressors have a high pressure rise stage that can be around 8 to 1, and generally centrifugal compressors are limited to two stages due to the efficiency concerns. The two main functional elements are the impeller and the diffuser. Although the diffuser is a separate unit and is placed inside and bolted to a manifold, the entire assembly, diffuser and manifold, is often referred to as the diffuser. For clarification, during the compressor familiarization, the units are treated individually, but the impeller is usually made from forged aluminum alloy, heat treated, machined, and smoothed out for a minimum flow restriction and turbulence. Now, in my experience, this is going to be the more common one. It's an axial flow compressor. So it's got two main elements: a rotor and a stator. So rotors will turn, stators stay. The rotor blades has blades fixed on a spindle. These blades impel air rearwards in the same manner as the propeller does, because their angle and their airflow contour, which is really important that whenever we get to blending blades, to remember that the way that you blend a propeller blade and the way that you blend a rotor blade is basically the same way. Anyways, as they turn at a high speed, it takes air at the compressor inlet and impels it through a series of stages. From the inlet to the exit, the air flows along an axial path and is compressed with a ratio of 25 to 1 or 1.25 to 1 per stage. So that's per stage. So every stage is getting a little bit tighter, a little bit tighter, a little bit tighter as it goes. The action of the rotor increases the compression of the air at each stage and accelerates it rearward through several stages. With this increased velocity, energy is transferred from the compressor to the air in the form of velocity energy. The stator blades act as diffusers at each stage, partially converting high velocity to pressure. Each consecutive pair of rotor and stator blades constitutes a pressure stage. The number of rows of blades or stages is determined by the amount of air and total pressure rise as required. Compressor pressure ratio increases with the number of compression stages, and most engines utilize up to 16 stages or more. This is whenever you see the engine cutaway, you'll see all those spinning blades and with the little stator blades on the inside. That's what's happening. What's happening here is that, like, as the air moves through from one stage to the next, it gets tighter and tighter and tighter and tighter and tighter until it gets ready to go into the next stage of the engine. Okay, so this is another thing that's kind of important for you guys, because you will take apart a turbine engine while you're here with us, and so I want you to see how these blades actually connect to the engine itself. There's going to be a rotor disc that's actually spinning around, and then those blades will slide in and out of that rotor disc. Now, in terms of maintenance, like, you're going to have to check these for dings, nicks, so on and so forth, and then blend those blades out so that way they are nice and smooth and able to It's able to move the air and compress it as needed. The other thing that you'll have to remember is to keep the engine in balance. Like you've ever washed like a put something in the wash machine and put all the clothes on one side and it starts to the centrifugal force starts to rock the wash machine and makes a bunch of noise. The same thing will happen here if those blades aren't balanced appropriately. So if you go out to our JT9s, you'll find that every one of those blades on the fan are balanced with another blade across the spinner that with the same grams. So it'll be like 400 grams, and the other one's like 401 grams or whatever. And then the blade next to it might be 350 grams, and the one across from it is about 350 grams. And all around those, you'll find across the spinner the the blades that have this most similar weight is what you'll get, and that's to keep it as evenly spinning as possible. If you get one that has like 400 grams on one side and 10 grams on the other side, it would shake it all to pieces. And with the RPMs and power that we're dealing with, it would absolutely just eat itself. So, in order to make it effective, that's what you have to do. And the way that you do that is by taking these blades out one at a time. And the way they come out is that they just slide right out of that disc, out of the root right there. Now, there's two kinds. You have the bulb on one side, which is just a big ball on the end of it. And then you have the fir tree, which has a bunch of little teeth that grip it and come in and go out. But that's your compressor section in a nutshell. Okay, here's the combustion section. Now we've gone from the air inlet, we've compressed the air, and now we're actually going to light fire to it. So the primary function of the combustion section is, of course, to burn the air to fuel mixture that adds heat energy to the air and helps the air start to expand, start to spin the next stage. To do this efficiently, the combustion chamber has to do four things. One is to provide the means of a proper mixing of fuel and air to good combustion. So we're going to talk about the igniters and the injectors here in just a second. We need to also burn the mixture efficiently. All right, so that means that like there's a certain size and shape of the flame that actually needs to happen right there, and you'll start to see that you'll get different power ratings, different EGTs, TGTs, if things are off just slightly in the combustion section, and that could be as simple as the spray nozzle is all coked up, or maybe the can's not sitting quite right correctly, and so you have to go in there and you have to fix these things after you do like an engine service. Then you need to cool the hot combustion products to a temperature that the turbine inlet guide vane blades can withstand operating under those conditions. So, in other words, it can turn around and light the fire, but if it gets too hot and starts melting the downtrace vanes, then that basically defeats the whole purpose. And then lastly, it needs to deliver the hot gases to the turbine section. It means there needs to be a way out, somewhere to go to spin it up. Okay, so now every combustion section is going to have five things in common. They're going to have a casing, an inner liner that is perforated, some sort of fuel injection system, some sort of means for initial ignition, and then a fuel drainage system. All right, now all of those can be rearranged into four basic different types of combustion chambers. There's the can type, like you're looking at here, that's a burner can, a can annular, an annular type, and a reverse flow type. So let's talk about the burner can first, and then we'll go over the other ones. Because once you understand the can, the rest of them kind of just fall into place. So a can type combustion chamber is typical of the type used on turboshafts or APUs. Each of the can type combustion chambers consists of an outer case or a housing that has perforated stainless steel combustion chambers liners or an inner liner. The outer case is then removed to facilitate liner replacement. So these liners will come and go as the engine gets worked on. So older engines with several combustion cans can have an interconnector tube, which has a necessary part, which is a necessary part of the can type combustion chamber. So that basically you can link all these cans together. All right, let's look at our can one more time. So the liners of these can-type combustors have these perforations. You can see the holes going all the way around them. They're all different sizes, and each hole has a very specific purpose and an effect on the flame, the shape, and the way it moves through the can in the liner. So the area entering the combustion chamber is divided into proper holes, louvers, slots, and there's two main streams that it's going to divide it up into: the primary and the secondary. Now the primary combustion area is directed inside of the canner at the front end, where it mixes with the fuel and is burned. Secondary or cooling air passes between the outer casing liner and it joins the combustion gases through larger holes towards the rear of the liner, cooling the combustion gases from about 3,500 degrees Fahrenheit to about 1,500 degrees Fahrenheit. Now, to aid in the atomization of the fuel, the holes are provided around the fuel nozzle in the dome of the air inlet of the can-type combustion liner, which is why making sure that the injector or the spray nozzle is in the right place. So it's oriented correctly to those holes and liners and louvers and all that good stuff. Now the louvers are also provided along the axial length of the liners to direct cooling layer of air along the side of the firewall. Because remember, it's not just about making the combustion side of it, but also cooling that hot air down low enough to where it can actually be used by somebody. Now, this layer of air tends to control the flame pattern by keeping it centered in the liner and thereby preventing the burning of the liner walls. This illustrates the annular combustion chamber liner. Some provision is always made in the combustion chamber case for installation of the fuel nozzle, and the fuel nozzle delivers the fuel into the liner in a finely atomized spray. The more spray that is atomized, the more rapid and efficient the burning process is. Whenever y'all do a fuel flow check on these things, you kind of hold up like a little Gatorade bottle or whatever to catch the fuel. You'll see it's like a mist. It's not even like a spray. It just kind of fogs fuel out, and that's to make it burn better. So just you increase the surface area of the droplet, and you increase the amount of oxygen that fuel is exposed to, and therefore you increase the rate in which it can burn. So it's a lot more efficiently. The finer you can get the droplets. So it's always a ratio between surface area and droplet size or mass. All right, now there are four types of combustion chambers that you will run into. First off is the one we've been talking about, the can. So the flame basically resides inside of that can and then moves backwards into the turbine section. Now the can annular has a shroud that effectively connects all of the cans, for lack of a better term, and that allows the flames to spread out more evenly across the cans before proceeding aft into the turbine section. The annular just bypasses the cans altogether and fires it off. Now there's a fourth type, it's a reverse flow combustor. And reverse flow combustors are a type of combustor in which the air from the compressor enters the combustor outer case and reverses its direction as it flows into the inner liner, and again reverses its direction before it flows through the turbine. Reverse flow combustors are used where the engine length is critical. So like for instance the helicopter engine I used to work on was a reverse flow combustor type, and you'll see that in places where you need to squish the engine together. You'll have that reverse flow combustor type where the can is more centralized. Okay, so now once we are through the combustion section, we're going to get into the turbine section. This is where all this work that's happened to the air and the fuel is really going to start to get harvested. We're going to start to see the benefit of it, because as that hot gas leaves the combustion section, it's going to flow over these turbine blades, and as it goes over the turbine blades, they're naturally going to want to spin because of Bernoulli's principle that, like, as you know, they're shaped like airfoils. The low pressure area on top of the airfoil is going to give way to the higher pressure area on the bottom of the airfoil and cause it to go up. However, this, just like a propeller, instead of going up because it's attached to that main shaft, is going to cause it to rotate. And as that happens across all of them, it starts to build this rotational speed higher and higher and higher. So it transforms a portion of the kinetic velocity, that kinetic energy of those exhaust gases, into mechanical energy to drive a gas generator and compressor up front. So as it starts to spin, it's actually going to help create the self-licking ice cream cone that is a jet engine. The sole purpose of the gas generator turbine is to absorb about 60 to 70% of the total pressure energy from the exhaust gases. The exact amount of energy absorption at the turbine is determined by the load the turbine is driving. and that means like all the accessories, all the stuff. And we haven't even got to the accessory gearbox yet, but the like anything that engine's tied to, be it a rotor blade, be it a big fan up front or a shaft or whatever. This is where all that energy comes from. There's an explosion. It goes over those turbines. The turbines turn to the shaft. The shaft then starts turning the front of the engine, and along the way it turns a drive gear that turns the accessory gearbox. It causes everything to work, and then everything that engine is running is stepped down by transmissions or gearing or whatever to the appropriate RPM. All right, now in the turbine section, there are three types of turbine blades. There's the impulse turbine blade, the reaction turbine blade, and the reaction impulse turbine blade. The impulse turbine blade is also referred to as a bucket. It's catching things. All right, this is because the stream of air strikes the center of the blade and it changes the direction of the energy as it causes the blade to rotate the disc in a rotor shaft. So imagine like sticking your hand out in a kind of a cupped fashion out the window, and you would catch that air. That same backwards push that's happening to you is, imagine like your body is the shaft and it starts to spin it around. All right, now the turbine nozzle guide vanes can usually be adjusted during engine overhaul and assembly in order to increase the efficiency of the airstream striking the blades or buckets of the turbine. So you'll go through there and make sure that they're all turned right, because over time things will move and shift and corrode and problems. And so whenever you're overhauling, you're trying to reset it and you'll get a lot of power back that you had lost over time. Now the reaction turbine blades cause the disc to rotate by the aerodynamic action of the airstream directed to flow past the blade at a particular angle in order to develop most efficient power from the turbine engine. The reaction impulse blade combines the action of both the impulse and the reaction blades. The blades more of the bucket shape of the impulse blade at the blade root, but it also has more of an airfoil shape of the reaction blade on the second half of towards the blade. So that is how those blades work. Now, the reality of it is that like you'll look in there, you'll see blades, and you're just like, okay, cool. Air goes over them and it starts to spin it. That's really kind of what you need to know. However, it is good to have a really good understanding of why it's working the way that it's working, because every engine is going to be slightly different and it's going to create different effects that you want to be cognizant of as you're working on it. And it also helps you with troubleshooting. The more you can understand the way that something works, the better troubleshooter you will be. And so seeing these different types of blades, if your engine's not developing enough power, you're getting certain types of problems, reactions, whatever, you'll be able to kind of think through the process of what's going on inside of that engine and what could potentially cause the problems that we're dealing with. All right, so this is a turbine blade. Notice that it has cooling holes on it, and you can see where it slides into the race that it's going to run on. That race will then be tied to the drive shaft, which will sit inside of some sort of bearing apparatus to allow it to turn over without a whole lot of friction. But these are your turbine blades. So whenever we start talking about potential engine problems and failures, like hot starts, think about like if you go over EGT for too long, you're going to overheat these things, cause them to expand, warp, or whatever, and it won't work properly after that. Or the worst case scenario, you have a catastrophic engine failure. Even the worst possible scenario is that happens later on. So you're flying along thinking that everything's fine. All of a sudden, these things finally just give way because you hot started the engine or ran it too hot for too long or something like that. But that's how precise some of these tolerances are. Those holes there are designed at the right place, at the right size for a very specific reason to help maintain a certain temperature in those fan blades. Okay, and the last component of all this is the exhaust section, effectively the tailpipe. Now, the exhaust section is really kind of going to come down to one thing. It's just heat management. And you're going to see a lot about, hey, like, if you look at this graphic, you'll see, hey, we got ram air coming here to help cool things off, kind of like an augmenter of sorts. You'll have induction air there, insulation blankets to keep the heat from leaving the engine and getting onto the airframe. Very, very important that you'll see on the inside of cowlings or asbestos insulation that will prevent any sort of superheating or spark, translation over onto the rest of the airframe. And then as it comes out, it's going to hit the outside air, and that's what actually really makes a lot of your noise. And we're going to get into more of that when we start talking about exhaust and hush kits and all that kind of thing. But essentially, for now, all you need to know is the exhaust section on a turbine engine simply just is that it's just exhaust. It's just hot air that just leaves. We've squeezed it. We've blown it up in the combustion section. We've extrapolated all the energy that we're going to be able to get from it, and now we just need to dump it so that way we can make room for the next set of air. And that is what the exhaust section of a turbine engine does.
All right, now that we understand how they work, the internal components, and all that good stuff, let's talk about the different types of turbine engines that you're going to come across out in the field. From turbo shafts, turbo props, turbojets. What are they, and why are they relevant? And how are they different to us as?
Okay, so there are four, it's technically five types of quote jet engines. When people talk about jet engines or turbine engines, this is what they're talking about. First off, is the most classic one, the oldest version of it is the turbojet. This is literally just it's going to compress the air in the front, it's going to bang it in the middle, and it's going to just shoot it out the back. There's not a whole lot more to it than that. This is like your old ME 262 Sabres. To a certain degree, the Learjet kind of falls into this category. Your F-16s, your F-22s, those they're a little bit more complicated than just a straight turbojet at this day and age, but that's the family they fall into. Now, the next thing that came about was the turboprop. All right, so people started realizing the turbojet is great if you want to go like just screaming fast, but it burns a lot of gas, and so they're like, this becomes like a theme with jet engines of like, how do we just deal with the fuel management but still utilize the advantages that the turbine engine gives us. And so we look at the turboprop next. That kind of comes around, and all this is that basically it's a jet engine, but instead of drawing its primary thrust from the exhaust leaving the aircraft, it turns a shaft, which then turns a prop, which gives excuse me, gives a lot of advantages to the aircraft. You can get by with a much smaller jet engine, so you have a much lower fuel burn, but then you still get a much greater performance than a piston engine. So it's kind of like this best of both worlds approach to turbine engines. However, you're still limited because you have a big prop out the front, so that you can get so much performance up to a certain point, but then the prop basically is also a big drag fan that kind of like caps the limit of performance. So then people are like, well, okay, now what do we do? If we wanted to fly up, to the 40,000 feet, what else can we do? And so you replace the turboprop with a fan up front on a fan cowl, and all of a sudden things start to become even more economical at altitude, and you still get the performance of the jet. Now, it doesn't go quite as fast as a turbo jet, but it's not quite as economical as a turboprop. It's kind of this middle ground where you get the turbofan. Now, the last one on this slide is the afterburning turbojet. So effectively, you go back to the turbojet, and it's just shooting flames out the back, and the last thing there, they just throw some more extra fuel into the afterburners, hence the name afterburners, and that extra kind of explosion helps push you that much further as long as you squeeze it correctly in the exhaust cowl. So that's your four main types. Now, there's one other one that we really need to talk to that's kind of related to a turboprop. All right, so this is a turbo shaft engine. Now, the primary difference that you're going to get from a turboprop engine and a turbo shaft engine is that this engine is built to still be linear. You can see where like there's the front end side of the engine that's going to take in the air, compress it down, and then you have these diffuser scrolls that are going to go all the way back to the combustion section, and it's going to blow the power forward and then up and then make a 90 and go to the exhaust off the top. So this is a real common helicopter engine. Now, the way that it generates its useful power, which the helicopter is actually going to use, is through the accessory gearbox that's actually on the bottom. So that big gray thing that you're looking on the bottom right hand side of the engine is actually the starter generator. Just to the right of it is going to be this the circular port that has these teeth in the gear. Well, that then marries up to a shaft which turns, and then turns the transmission, that turns the actual rotor head and all the good stuff. And so it's very similar to a turbo prop that's that's doing effectively the same thing, but it's set up so that way it can turn a shaft that can turn in both directions, so it can turn both the tail rotor and the main rotor of the transmission and all other good stuff. And so that's technically a fifth type of turbine engine, even though it's very similar to a turboprop, just redirected the power in different ways.
All right, lastly, let's talk about auxiliary power units, or APUs. Where do we find them and what are they for?
Okay, lastly, we're going to talk about the APU, the Auxiliary Power Unit. And all this is a very small jet engine, usually located in the tail of the aircraft, that helps supply ground power whenever the engines aren't running. So it has a lesser fuel burn, but it still supplies enough electrical and air and hydraulic power to the different things on the aircraft that you may need for maintenance or to cool the aircraft off before somebody gets on board. So, like, let's say if you were to try to take a bunch of people flying, you would want to get on there. The plane's going to be super hot. It's been sitting out there baking in the sun. And the first thing you're going to do is just turn battery power on, then turn the APU power on. And that's going to get everything up and running and all that stuff. Now, you're not going to get the full AC effect because you don't have the engines running that's going to run the passenger air conditioners or the packs. But you can get some air moving on the inside that at least helps start to kind of cool it off. And it gets your electrical power up to the point that you can actually turn, engine one, turn engine two. It'll get hydraulic pressure if you need to run any kind of maintenance checks for your flight controls, all that good stuff. And that's all the APU effectively is. It's just kind of like a micro jet engine in the aft end of the aircraft, so that way you can run it without turning on the main engines. Because when you turn the main engines on, you have to worry about what air, are you going to suck something into the engine, what's going out the back, how much fuel we're burning, all that stuff. The APU is really just for ground handling, and it also has the added benefit of being able to be a backup power source. So if, like, say you're flying along and boom, like, you lose both engines for whatever reason, you can always turn the APU on, and that gives you enough power to work the radios, gives you hydraulic power to fly the airplane to where it's going, all that kind of stuff. And so the APU is nested, and we've talked about it before about how it's nested into the power distribution network of the aircraft. But it also has just a redundancy effect for pretty much all systems, because it's effectively just a third engine back there that just doesn't provide thrust.